This is CP233, lecture 15, example 2. This is going to be a little bit shorter example than the last one. This represents a redo of the previous example 2 because that was wrong. I discovered that a while ago. So went through 2 quarters teaching the wrong stuff. But anyway, this will be right this time. So let's look at this. Maybe. Okay, and so what we're interested in is these are microcontrollers and they control things. So it's an issue of how many unique bits can it, we'll say, control, and how many unique bits can it control also. So essentially on the input, generally speaking, you're inputting like status bits from some part of the circuit. On the output, you're outputting control bits. So you're reading some status, you're sending out the appropriate control bits. So that's input and output. And so these are very, well, that's remotely similar, but let's take a look at these. So I'm hoping that you get a really good intuitive feel for this, because that's essentially, that means you don't have to memorize this stuff, and we'll go from there. Okay, so this is the top level microcontroller black box diagram. You can see it has about 100 inputs, and so we've got data coming in, got data coming out, and we got an address. Those are the majority of those 100 inputs, and that's essentially what we're going to mostly talk about today. Okay, so this is essentially, this is all you get right here, but if you were limited to 32 inputs and 32 outputs, it would just be, in many cases, be totally worthless. So what we want to do is be able to control a hell of a lot more inputs than what's kind of apparent from this thing. And so what it's done is the RISC-V microcontroller is very generic in the way it handles I/O, and that's what we want to talk about here. So the issue is how many, according to what we have, a RISC-V Otter, which is essentially limited to a specific amount of program memory, actual memory, how much I/O do we have? And they're really closely related. So if you look at this diagram down here, this is the key here. We got addresses. We have addresses that are used for both input and output. Certainly, you could imagine them being used at the same time for input and output, but that's generally not what we do. The instructions are either inputting a value, which it does with a load instruction, or it's outputting a value, which it does with some type of store instruction. And so here is the external world on the inputs. It can, on our Basis 3 board, we have 16 switches and a various amount of buttons, up to 5 buttons. I didn't put a number there because the wrapper kind of uses them different ways. It uses a button for a reset, and later we're going to use a button for the interrupt, but don't have to worry about that now. Essentially, you just have a ton of inputs on this thing. We only have 20-ish, but in real life, I want to know how many you can have. And that's what this question is asking. So this is a MUX here. The select signals for the MUX are the address. So technically speaking, there's going to be, since it's 32-bit address space, there's technically going to be possibly a lot of inputs here. So these address bits are going to choose which of these data actually makes it into the microcontroller. So what we're interested in is how many addresses, or how many unique addresses can I use for the select inputs on this input MUX. Now the issue for this is you have to remember that this is memory mapped I/O, and the I/O doesn't know the difference between memory reads and memory writes. So what we're interested in is how much memory does this actually have, and this is going to be, it's going to be 0x1 2 3 4 5 6 7 8 through 0x 0 0 0 0 f f f f. Okay, so that's the physical memory range for the RISC-V Otter. Those addresses, when I access those addresses, the memory is going to say, oh, they're doing a memory access. They're not doing I/O. Okay, so every other address besides this is going to be dedicated to I/O. Now, so what we're interested in is how many addresses are dedicated to I/O, and that's going to be the entire range, 0x f f f f f minus 0x f 0 0 0 0 f. Okay, so this is going to be the number of addresses available for essentially for input. Okay, so those, that's some huge number. I don't know what the number is. Those are the number of unique addresses that are not accessing physical memory, and because they're not accessing physical memory, they can be used for I/O. That is the number of addresses. So at each of those addresses, I have the ability to input, get this, 32 bits. Okay, so that means this many unique addresses right here times 32 bits, and this number right here is going to be number of unique inputs. Input bits, I forgot what I said on there. How many bits can it manage? This is the number right here. Now, so the issue is that it's going to be very much the same for the output, and the idea here is that here are the output, the width of the output, very much like the input, is 32 bits. And how many unique addresses do I have? Well, once again, it's the number of unique addresses dedicated to output is going to be essentially the number of unique addresses minus the ones that are dedicated to memory. So that's going to be this value once again. And so so it's going to be this value for output, and then it's also going to be times 32. So what you see here is it's the same number of bits for input and output on this thing. And certainly the issue here is that the output here are registered, so they're persistent. I have to register them to make them persistent. No need for a register on the input. That data just feeds into the register. Here, the output, it's going to take data from a register, kind of toss it out to the outside world. And what I like to say here is this is a decoder, and this is essentially which selects which one of these I am going to write to, and this is the actual write signal. So once again, the address bits are selecting which register I'm going to write to. The write signal here actually controls that writing. And I will call that done for this problem, and we'll do one more example problem after this.